All right, so beginning our lecture on chapter 16, second chapter on the sun. This one's all about powering the sun. How does the sun glow? Well, it has to do with atoms and atomic nuclei, as you've probably picked up on. So, modern nuclear power. Now, let's just lay the groundwork here. Modern nuclear power plants generate energy by, here are your options. Thumbs up for combining atoms into a new type of atom. Thumbs down for splitting an atom into many new atoms. How does a nuclear power plant work? Like the one near Sacramento, right? It's one out or Stockton or something. There's a nuclear power plant near the Bay Area, which is recently reopened, as if I remember the news correctly. Hey, everybody says that it's thumbs down for splitting into many atoms. And you are right. Excellent. That is how we make nuclear power. It's called fission. All right, so it's the same physical process that was used for the bombs that the United States dropped on Imperial Japan during World War II. Okay, so we took that technology and applied it to a less destructive but still controversial source of energy. And the process has remained fission the whole time, not because the nuclear process of combining is impossible, as we will soon learn, but has proved very difficult. And fusion has remained elusive as a source of energy. So, quick history on fission, since it was discovered first. Fission, the splitting of one atom into many others, was discovered in 1938 by Lise Meitner in a basically atomic lab studying minerals and other naturally occurring heavy elements. What happens in this nuclear process, almost like in a chemical equation, but this being a nuclear equation, the original nuclear mass is greater than the mass of the two products or daughters of the fission. So when you have nuclear fission, that can be sort of stimulated or can occur spontaneously, because it indeed is a thing, spontaneous nuclear fission. It's not primarily what we think of, and it's not what nuclear power plants do. They have stimulated nuclear fission. But every time with these heavy elements, you have this inequality in mass. In other words, the original big nucleus has more mass than the two daughters. Okay, and they're not necessarily balanced. They absolutely can have different atomic numbers. They can have different atomic masses as well, or different both. They just has to be a split. What is balanced, so to speak, is the actual total number of protons and neutrons. So however many protons and neutrons make up the original nucleus will equal the sum of the two daughter nuclei, the products. I use daughter to represent products. It's a common terminology. Okay, so it's like the parent and the daughters. Okay, so if the number of protons and neutrons is unchanged, how can the mass change? Well, that's because it turns out that protons and neutrons don't really have mass in the way that we think about them. They have a certain amount of binding energy associated with them. One way to phrase this, which potentially could be confusing, but might help you understand it, is that the protons and neutrons in the larger nucleus weigh more individually. They have more mass per nucleon. So when you split them into the smaller nuclei, the individual protons and neutrons now have less mass per nucleon. Remember, nucleon is a collective term for everything in the nucleus, namely neutrons and protons. So it's like each one now has less mass. And what that means is that it's that bind, that thing that holds them together. In other words, the idea of them having less mass is obviously a foreign idea. How could a particle have less mass if it's the same particle? It's because the nature of that particle is not independent of where it is. That particle is not a defined entity on its own. It matters where it's located, what type of nucleus, what type of energy environment it's in. So often the term binding energy will be used. Now, in maybe a more practical, although still very high-minded sense, this loss of mass is converted into energy, and that relationship is related by at least I can say, honestly, a very simple formula, E equals mc squared. Simple to work with, simple to calculate, where E refers to the loss of mass, so the mass that was in the bigger original nucleus and now no longer exists within the sum of the products. All right. So that's the so E is the sorry, I kind of missaid that. So M is the mass, E is the energy that's released, and then M is the change in mass. So M is the change in mass. You could kind of say that M is equal to delta M, if you're familiar with that notation, because it's really not just a fixed amount of mass when you use this equation. It's always represents a change. It's how much mass was lost. So the M represents the lost mass. One other way to write it would be say that M is equal to M subscript lost. But with a little bit of practice, since you only ever use it to refer to a change in mass, it might become natural just to think of it as M. That's the way that I would like you to think of it. And the idea then is that change in mass then can be directly related to an energy in joules, no less, as written. This is all base units. And the only thing needed to do that is one little proportionality, which is the speed of light squared. As long as you multiply the M by the speed of light squared, you'll get the energy that is created, in a sense, okay, from the loss of mass. And C, of course, is the speed of light, which is 2.99 times 10 to the 8 meters per second. So I say that the energy is created with hesitation because you might know that energy cannot be created or destroyed. So what do I mean when I say the energy is created? Well, the energy appears to be created until you take note of one of Einstein's great findings, because of course that's where this equation comes from Einstein's publication on special relativity. And you then realize that energy and mass are part of a continuum. And so our conversion, or conservation rather, is not just energy, but rather a energy mass duality. So collectively, they're conserved. Yes, energy appears to come from nowhere, but no, it didn't. It came from the mass itself. Because what is mass? Mass is just binding energy, to take it back to an idea I said before. So if mass is simply binding energy, well, then that's your energy. The mass is energy in disguise. So with that quick rundown on some, wild modern physics ideas about nuclear energy and the relationship between energy and mass, let's get back to the basics. The sun generates energy, well, with fission, which is this one, or thumbs up, combining atoms. I bet you know. Let me just quickly get your answer here. All right, Alexander. Nick went for a cool kind of like a hang loose thumbs up. I like it. All right. Seems appropriate for this hopefully obvious answer. It's because the sun does fusion. Said it a few times, right? That's what the sun does. Two nuclei combine into a new nucleus. So it's the opposite of fission. It's bringing things together instead of splitting them apart. Fusion, okay, two nuclei combining into a new one, was discovered back in a little bit later in the 1920s by Sir Arthur Eddington as a source of solar energy. Okay, it was proposed as how the sun creates this energy. Before this time, it was a very open question and a hotly debated question about how the sun produces energy, with many smart scientists not leaning towards fusion because it was unknown, unproven, right? Seemed like a big stretch to come up with a whole new branch of physical processes, a whole new branch of physics, if you will, to explain the energy source of the sun, when other well-known energy sources, conventional energy sources, seemed, if not more likely, at least less, less intimidating or less far-fetched, right? In a sense, so although it's easy to laugh at scientists now and say, well, how could they have thought it was anything else? I think it's important to remember how it must have been such a big leap into the dark to come up with a whole new idea of fusion, okay? Because proposing it as an energy source before we had really proven that it really existed and could be replicated in a lab is a big step to take. When fusion happens, there's the input are two nuclei. These are going to be low mass nuclei. We'll come back to that idea that with fission, we always start with something big, and with fusion, we start with two small nuclei. That's not just by chance, although it's possible to fuse big things and possible to cause fission of small things. We'll see there's certainly going to be a good reason about why that rarely happens. The product is a new nucleus that is bigger in terms of having higher atomic number, more nucleons. What is not bigger is its mass. So the inequality faces the same way in that the input is more massive than the output. So mass is lost with fusion, just as mass is lost with fission. And that's because we're talking about energetically favorable versions of both. What I mean is we're talking about versions of fission that produce energy rather than take it in or absorb it. We're talking about fusion as a way to produce energy. After all, it was proposed as the source of the energy from the sun. So that means it has to be somewhere for it to come from. It comes from the mass, the binding energy, which is mass. Okay, so the lost mass is converted into energy because mass is just energy in disguise. Well, that means it's going to be a lot of energy. And this was crucial for the explanation that it had to be the source of energy of the sun, because the sun was producing a huge amount of energy based off of modern calculations in the 1920s. And there really was no explanation of where that was coming from. If it came from a chemical reaction, then the sun could only be a few thousand years old. Right? Some people liked that because it supported a 5,000-year-old Earth, but certainly contradicted a lot of other findings. So we had to come up with another explanation. And the numbers worked out, but are still quite striking. The sun uses a huge amount of mass. And by uses, I mean this mass ceases to exist. 600 million tons of hydrogen simply disappear from the sun every second. That means the sun is becoming 600 million tons lighter every single second. When you hear that, you might say, that just can't be right. The sun would just, disappear after a while. Well, remember, the sun is 10 to the 30 kilograms in mass. So it turns out that even though this seems like a huge number, it's still many powers of 10 less than the overall mass. And once you realize how many, you can see then that it's not going to significantly affect the mass of the sun. It's that the sun is so big, it can lose this much mass and not really, change in its significantly over time, which is important because all of our orbits, the orbits that we count on not changing over hundreds of millions and even billions of years, depend on the sun remaining essentially the same mass. And indeed, this rate validates and guarantees that. The output of such a huge amount of mass, at least, compared to masses that we're used to as humans, is 4 times 10 to the 26 watts. So this is the wattage of the sun, the same way we talk about like a 60-watt light bulb. Remember, watts are just joules per second. So a joule per second. This is how many joules, 4 times 10 to the 26, the sun produces every single second. That term, wattage, in astronomy is called luminosity. So the official astronomical term for power is luminosity. You can just call it power if you want. You can call it wattage. I'll know what you mean. But it is important because we have a lot of similar terms here when we do talk about light to, at least try to clarify what the astronomical terms are. And luminosity is one of those. I want us to think about it in the context of intensity, as well as like energy flux, which we saw before, because they're all related. We'll probably get some more practice with that soon in the homework, but do look into it in the textbook as well. So there's still enough hydrogen in it for another 5 billion years. So what I mean by that is, do I mean like that enough hydrogen, like the sun's not going to like waste away in 5 billion years? No, that's not what we're talking about, but actually still have enough hydrogen in the core where it's hot enough for fusion to occur for the next 5 billion years. Okay? And the sun is 4.5 billion years old at this point, which means that its entire lifespan of burning, quote unquote, hydrogen, and by burning, I mean fusing, okay? And literally, it's the same fusion that is represented in our kind of default figure for fusion, showing 2 individual particles coming together. Don't worry about their colors. They're going to both be protons in our case. But in order for the sun to still have, enough hydrogen, it will reach a age of 9.5 billion years. At that age, it will run out of available hydrogen in its core. Its mass will still have not sufficient or significantly changed, but its core, a small amount of it, overall hydrogen is in its core where it can actively be fused. And that's where it matters for this idea of it running out of fuel. Okay? At that point, the sun will transition to a new life stage, which is much shorter, and it will become a red giant. Still millions of years, hundreds of millions of years, but not billions. All right? Well before, in terms of, a billion years, but of course that's only 1/5 of the remaining hydrogen phase of our sun, the galaxy that we live in, the Milky Way galaxy, will collide with the Andromeda galaxy. So this might seem like a non sequitur. Why are suddenly we talking about galactic collisions when we were talking about fusion and the lifespan of the sun? Just to give you a idea about fun thinking about what will happen first. Does that mean that we're going to get destroyed or the galaxy is just going to, get obliterated when they collide? Absolutely not. Almost certainly our solar system will be just fine. We'll have a new night sky that will, be changing over a faster span of time relatively than it is now. But overall, individual stars will not collide with each other. They'll just, have new orbits. And it just will happen to happen a billion years before our sun transitions to its red giant phase. So, knowledge recall, kind of going back to some of those early chapters, right? The particles inside the nucleus of atoms are, you've been paying attention, you know this? Yeah. Alexander got it. Yep, Nick, you know it. Protons and neutrons. Oh, yep. Also, acknowledge all these right answers here. Yep, Isabel, nicely done. Jay. Yep, not positrons. Right? Kind of there to fool you, right? Put it first. If you're in a rush, you might choose that one. But no, you know it's protons. Positrons are a real thing. I know they might sound made up. They're actually produced in the fusion process that currently occurs inside the sun. We'll talk about them later. They're called antiparticles because yes, antimatter is real. It just tends to not last very long. So, but that positrons are an example of antimatter. But protons are not. Protons are ordinary matter. So are neutrons for that matter. For that matter, they're matter. All right. Electrons, none of them inside the nucleus. Okay. Here's an example of a atomic nucleus. Protons have a positive charge. Neutrons, no surprise, are neutral. That's the name, right? So if you have 4 protons, then that defines your elemental name. So the number of protons sets the name on the periodic table, not the number of neutrons, not the combined number of protons or neutrons. Just protons alone defines that element. That makes practical sense because that really is going to relate most directly to the electrons, and the electrons are what matter for chemistry, which is why the periodic table was created in the first place. There's no major issue that atomic physics has with still, working with that. It's a perfectly good convention to say that it's the number of protons that really kind of sets some of the most important characteristics about an atom. Just remember that the caveat is that mostly has to do with what the electrons are going to be doing, because a neutral atom will have an equal number of electrons. There's a whole idea of electron shells and how they get filled and how that can lead to different types of bonds because of the different shells and their shapes and things like noble gases. Okay, but does that matter for nuclear physics? Not really. When we talk about the sun, all of our atoms are going to be totally ionized. Electrons just don't seem to exist because they've all been pushed away. They're probably that's where the solar wind comes from, right? All those electrons that constitute the solar wind. Where do you think they all came from? They came from ionizing all the atoms. So when we talk about atoms in the context of nuclear physics and solar energy, it's like just no electrons there. All right. So do we really then care about the fact that protons define the element? I don't know. Kind of. We'll see more isotopes than you would in a discussion of chemistry, that's for sure. So keep that in mind, that lots of times we end up with these particular isotopes, and we just got to, think that's kind of what matters. So when we talk about beryllium, what type of beryllium is it? Is it beryllium with 4 neutrons, which would be beryllium-8, or is it something else? But I'm getting ahead of myself, so let's continue with our naming. Okay. Now, if we take our beryllium with 4 protons and we take 5 neutrons, we end up with a total of 9 nucleons, and we have our standard stable beryllium, beryllium-9. Not a terribly common element. There's some good reasons for that. If you look at the current homework problem that's posted, or homework assignment, homework 7, I discussed beryllium a little bit because it's produced in red giants like our sun will eventually become. And the beryllium that's made in that case is beryllium-8. Okay, beryllium-8 would not have 5 neutrons, but instead would have 4. And that type of beryllium we say is unstable. This beryllium is stable. Both of them are beryllium. Just to make that clear again. The only difference is that they are different isotopes. They're technically both isotopes. Any combination of neutrons with a certain number of protons defining the element is an isotope. However, the most common version of an element, the type that is the default, often isn't referred to as an isotope. It's just the element, right? So you've got the element and then isotopes of that element. That can get confusing because then you wonder, is there some special thing that isn't an isotope? No, it's just that because that's the standard version, we don't bother calling it an isotope. We just call the unusual versions, usually the kinds that don't last long because of their instability, We called them the isotopes. Or remember hydrogen, right? Hydrogen standard is just one proton. Is that an isotope? Yes, technically it is. But deuterium is often referred to as the isotope of hydrogen, the version of hydrogen that has a neutron instead of no neutrons. So you get kind of how the terms get used. But again, officially, every combination is an isotope. Okay, same atom, different number of neutrons. Okay, different, not compared to anything, just specified. So which isotope of beryllium has the most neutrons? Beryllium 7, beryllium 9, or beryllium 10? Tell me. I want to make sure you understand this. So let's get some answers. Once I started talking about isotopes, y'all said no. Done. Done with astronomy. Okay. Thank you. Thank you, Nick. Anybody else? Okay, okay. 2 votes for 3. Beryllium 10. Okay. Hey. Well, it turns out you are absolutely right. Looks like this. Beryllium 10 is the one at the bottom. Okay, the 10 refers to the sum. Since 4 couldn't change because it wouldn't be beryllium otherwise, beryllium 10 has to have 6 neutrons. Okay, that's the idea. So to be able to do this, right, to look at these 3, which all exist, right, these are all types of beryllium, all isotopes of beryllium, you have to know what is the atomic number of beryllium. And the atomic number is the number of protons. So you'd look that up, or you'd have a periodic table handy where you would see the B and you'd see next to it the 4, right? So that's necessary information that isn't just like immediately obvious when you read the word. So in other words, you need to be able to translate beryllium into 4 protons. So when particles with the same electric charge get close together, they do what? Remember your basic rules about electromagnetism. All right, Nick, when Whiteford, they repel each other. Everyone agrees? All right, Jay, nice. Absolutely. Opposites attract, like charges repel. Just don't forget that gravity is different. Gravity, everything attracts. Gravity is only attractive. So that means that inside of the nucleus, and this is kind of, I've always thought this is fascinating, right? Because it just makes you wonder. All the protons inside the nucleus repel each other. But the nucleus is literally like a packed together clump of protons with neutrons, which don't do anything. So there's nothing to balance this repulsion. How is it that all these protons are able to get packed together so tightly and not just tear apart the nucleus? What holds the nucleus together? Well, there's a force called the strong nuclear force, which is a totally separate force from gravity and electromagnetism. It is a fundamental force of the universe. Again, separate from gravity or electromagnetism. It only applies to the nuclei. It has an incredibly short range of interaction, a short range of effectiveness. But within that range, it is stronger than the electromagnetic force and is the strongest force in the universe. Just doesn't extend very far. And it's what holds the nucleus together. Okay, if it wasn't for the strong nuclear force, nuclei wouldn't exist. Why the strong nuclear force is a thing is just part of the fundamental fabric of the universe. It was one of the original forces that separated out from the grand unified force after the Big Bang. And it just defines the way physics works, just like gravity and electromagnetism. So within that atom, okay, the subatomic particles are protons, neutrons, and electrons. The electrons, they're outside the nucleus. They're attracted to the positive charge of the nucleus. Okay? They don't need another explanation. We don't need the strong nuclear force to explain why electrons orbit the nucleus. That's just electromagnetism. Okay? So strong nuclear force holds the nuclei together, which otherwise would seem to want to tear itself apart. And electromagnetic force binds together atoms because the electrons held to the nucleus then can interact with other nuclei and have weaker bonds that pull together atoms, creating molecules. As if that wasn't enough, there is one more force. And this is it. There are only 4 fundamental forces that are known to modern science. And the last of these 4 forces is called the weak nuclear force. Just like the strong nuclear force, it only applies, I was going to say holds, but no, it only applies to the nucleus. It doesn't exist outside of atomic nuclei. It also has a very short range of effectiveness. And it is responsible for radioactive decay. Now, not all types, mind you, but beta decay, which was the type of radioactive decay, which we did briefly discuss, which involved the emission of electrons or positrons from the nucleus. And it always involved the conversion of a neutron into a proton or a proton into a neutron. So we can think of the weak nuclear force as being involved with these blue spheres becoming the red spheres or vice versa. Okay, so in other words, it operates at the scale of individual nucleons, whereas the strong nuclear force operates at the scale of the nucleus as a whole. In other words, the weak nuclear force is a smaller scale force, and it's also, as the name implies, weaker, although still much, much stronger than gravity, which is by far the weakest force. So if you wanted to name forces, maybe you could, have the weak nuclear force and then just the super weak force instead of calling it gravity. Okay, so here's gravity, holds together solar systems, galaxies, planets. Okay, by far so much weaker than all 3 of the other forces. And we're talking billions of times weaker. But the thing about gravity that sets it apart from the other 3 of the 4 fundamental forces is that unlike the electromagnetic force, it can only attract. And unlike either of the nuclear forces, it's not restricted to the nucleus, which means that gravity is the tortoise in the tortoise and the hare race, at least if the electromagnetic force is the hare, because electromagnetic force bounces around much stronger, but ends up canceling itself out and never winning the race because it never gets anywhere. Gravity is slow and weak and doesn't move fast, which is the same as slow. But given enough time, it just keeps accumulating. There's nothing to oppose it because it can only attract, and it just keeps pulling things in. So gravity will always win in the end. Take black holes as a great example. All right. So right there, before we get into more about fusion and how these forces are going to help us understand things and not just seem like a confusing distraction, we are going to take our 5-minute break at the midpoint of our class. All right, so we've been talking about the 4 fundamental forces And now getting back to fusion. Of course, fusion is not a fundamental force. It is a nuclear reaction. But how does it relate to all of this? Well, far apart, protons will repel each other. That's because of the electromagnetic force. Okay, so under most conditions, two protons will not crash into each other because the electromagnetic force means that their repulsion will just not allow them to get that close. But if they can be forced to, if you can create an environment where two protons will, because of their high velocities, be able to get within 10 to the negative 15 meters of each other, then the strong nuclear force takes over. So it's like you pass over this threshold, and as soon as the strong nuclear force becomes effective, it also dominates. So even though the electromagnetic force, of course, scales up with decreasing distance, so it's inversely proportional to the square of distance. So the electromagnetic force continues to get stronger and stronger the closer you bring the protons together, which is all the more reason they don't want to get that close. But at some point, all of a sudden, you hit that threshold, and the strong nuclear force goes from 0 to 60, so to speak. And then that 60 is more than enough to overcome the quite strong electromagnetic force, because the strong nuclear force is stronger still. And then they will stick together. They will create a new nucleus. And that is what will bind them together and is the basic idea of fusion. So that means that you have to have a lot of temperature to create those thermal velocities to get this, this approach, right? To get such a close approach distance, the way to do that is to have high velocity. You can like kind of modern fusion techniques, or kind of try to direct that high velocity, or create a very, very concentrated high temperature area with lasers. But it's always going to come down to just having a really energetic environment, really energetic individual protons, so that they're moving around so fast that they can actually get this close to each other, and therefore have fusion occur. Okay, so the temperature that is necessary inside of the sun to maintain the fusion of hydrogen is 15 million Kelvin. So that's the threshold temperature for hydrogen fusion. And we'll learn the other types of fusion all require higher temperatures. And so, we really there's kind of some lower temperature fusion, but really the majority of other fusions we talk about are going to be all at higher temperatures still, and usually involve heavier elements. Okay. And even within, this temperature range, if it goes up slightly, then that's going to cause the fusion rate to increase as well. So one idea that we're going to be seeing a lot more of, so don't worry about it too much right now, is the HR diagram. This is sort of a soft introduction to this very important diagram. If you remember, I compared it before to the periodic table. So I said that the HR diagram is to stellar astronomy as the periodic table is to chemistry, because it's this one diagram that summarizes so much of the discipline. I say stellar astronomy because we don't care about it if we're just studying, say solar system astronomy. But if we talk about stars, which anything beyond the solar system is going to involve, then this is super important way to understand stars. And the diagram is really a graph, and it relates luminosity on the vertical axis to temperature on the horizontal axis. And the group of stars that dominates the actual population of stars in the universe as a whole, and our galaxy being no exception, but also dominates the diagram, is called the main sequence, which is a pretty appropriate name. It's a diagonal swath of stars, which is here also surrounded by a shading to kind of show that the black dots are examples, but they could exist anywhere within this purple region. And stars on the main sequence can have high luminosity and live a fairly long time, all right, in terms of I guess, human lifespans, but relatively short as far as stars go. And then on the other end of the main sequence, we have stars that live a very, very, very long time. So we're talking lifespans that are much older than the current age of the universe. These are stars that almost might as well be immortal compared to the universe because they're going to live like 100 billion years based on our understanding of their fusion rates. So they're the ultimate slow and steady fusions. Not slow and steady gravity, but slow and steady fusion. Just turning the hydrogen into fusion at a real gradual rate, but quite sustainable. So, fusion throughout the main sequence. And by the way, just to point out that what actually defines the main sequence, and probably the reason that we kind of are going to start talking about it now, is all the stars in this population are doing exactly what I've been talking about, namely what our sun is doing, which is fusing hydrogen into helium. That particular form of fusion is exactly what a main sequence star does by definition. The other populations of stars are going to be over here and here and here and so on, and even down here. And these different types of stars all do some other process. Either no fusion at all, which means they're not really stars, so we kind of call them stars, or fusing other elements into other elements, like helium into carbon, or carbon into oxygen, or kind of helium into oxygen via carbon, but or oxygen into silicon, and so on. Right? So these are all the different types of fusions that can occur, but those would not be main sequence stars if they're doing that other type of fusion. So now more on the process of fusion. So the type of fusion that occurs in the sun is called the proton-proton chain. This is literally the fusion that we're going to be talking about the most. It's also for short called the PP chain. So P for proton. All right, there are 3 steps to the process. In other words, we start with hydrogen and we get helium as our product. But to do that, to go from hydrogen to helium-4, why helium-4? Because it's got 4 nucleons, all right? We have to go through these various steps. And different things happen at the different steps. There are essentially byproducts, and there's also a way that the steps explain the continual nature of the chain. In other words, the way that it can sustain itself and still, kind of keep the process going. You can see another type of fusion chain in the current homework assignment, homework 7. Also for reference, and because it's the same calculations, but different fusion process, the homework document that I posted the solutions for is exactly the proton-proton chain, if you want to see the numerical approach to this fusion chain. So let's go through it one step at a time. So the first step of the chain, shown right here, is the proton to deuterium fusion. So 2 hydrogens, hydrogen 1, which we call a proton more often than hydrogen 1. Okay, so it's just that case where whatever one term is one out as more popular, more easy to roll off the tongue than the other. So a proton is hydrogen 1, which might already seem obvious to some of you, but it's worth taking a moment to appreciate that, because literally it's true. It's ionized hydrogen 1, to be fair, but when we talk about, the name of the element, we don't specify whether it's ionized or not. That's only if we worry about the chemistry. So there's no electron, as just last time I'll say that probably, but I just want to make that clear. There's no electrons involved. So, okay, so it's just the nucleus, and the nucleus of hydrogen 1 is just a single proton. So it's literally just a proton, but it's also hydrogen 1. Okay, so the proton is a hydrogen 1 nuclei or nucleus. Anyway, 2 of them come together. Okay, they're going to fuse. They're going to overcome that repulsive force because of that 15 million degrees Kelvin. Well, I slipped up. Try not to do that. 15 million Kelvin, because Kelvin is not degrees. You just say 15 million Kelvin. You only say degrees if you're using Celsius or Fahrenheit. Fun fact. Anyway, they're going to come together at 15 million Kelvin. And what does the fusion mean? Okay, well, we know it means that there's going to be some change in the mass because you can't become a new nucleus without a change in that binding energy. That binding energy, which now I can safely say is associated with the strong nuclear force. Okay, you can, kind of reason that out for yourself. The product of the fusion is a deuterium nucleus. Okay, so that is hydrogen 2. So deuterium is another name for hydrogen 2. Okay, called hydrogen 2 because it's got 2 nucleons now. So this is an isotope of hydrogen. It is naturally occurring. Deuterium is stable and there, exists, throughout the universe, including on Earth, but it's quite rare. There are also 2 other byproducts of the first step of the proton-proton chain. And those are going to be a neutrino and a positron. And I think, so I bet the neutrino is the pink one because I'm thinking, because blue is going to represent positive. And this is the positron. So positron. And I know that we'll talk about the neutrino later. I saw in the slides. And I think we'll come back to the positron. But you can see it in the previous homework as well. But the names here, neutrino and positron. So these are both particles. They're not your typical subatomic particles. These are more exotic particles. And they're important for, in the case of neutrino, conservation of angular momentum. That's kind of how they were discovered. And that's, you could say, the role they play. The positron has to do with conservation of charge. And that's why it has to be created. Otherwise, if it wasn't, this process would violate a fundamental conservation law of physics, which is the conservation of charge. And we can start to see that being established here because the initial charge is +2. All right. And the positron has the mass of an electron, but the charge of a proton. So it's got one fundamental charge, which is a certain amount of coulombs, so it's not some, abstract idea. It's a quantifiable amount. But it has a mass that is much less. It has the mass of an electron, which is less than a 2,000th the mass of a proton. So electrons are not zero, but they're very light. Neutrinos are much lighter still. They're about 1,000,000 times lighter than an electron. So a huge, huge, huge difference. Regardless, they kind of have a measurable mass, especially with really cutting edge, last like kind of 10 years of experimentation. There's really kind of been an agreed value for the mass of the neutrino. Before they were assumed to be, have mass, but be so small that it was impractical to ever know what their mass was. But of course, we improve our techniques and now we do actually have a way to quantify their mass. The electron at some point was probably thought of the same way, too small to measure, right? So what is the electric charge of a deuterium? Because remember, we started with two charges. I've hinted at that we're going to, have an explanation of why the positron must be there. But before we get there, answer this question. What is the electric charge of a deuterium nucleus? Shown right there. What is its charge? Yep, no problem, Isabel. But anyone want to answer the question? Insane. Yep, you too. You too. Jay says 2. All right. Want to move along? So you are right. Absolutely. It's just +1 because that neutron doesn't contribute. That's just +1. So that means that we have a kind of a imbalance, right? If the deuterium is only +1, but we had 2 protons coming in the first place, then now we see why we have to have the positron. Okay, so the total charge has to stay the same. This is one of those fundamental conservation laws in physics and therefore in astronomy. Charge has to be conserved. So if we have just +1 coming from the deuterium, we need another +1, hence the positron. It's just like an electron, but has +1 charge. Okay? So you can imagine that people, came up with the theory of this before they were actually able to prove it experimentally, but it now has been absolutely experimentally proven. And this is how the first step of proton-proton chain fusion occurs. Okay? Okay. And there's that neutrino, no charge, low mass. Why do we need it? Right? Well, like I said before, it has to do with conservation of angular momentum, which is plainly put beyond the scope of the class. Okay. We're not, I burden you with enough physics as it is. We don't need to get into an understanding of angular momentum. But surprisingly for a lot of people, because you wouldn't, guess at first blush that something called angular momentum plays such a fundamental role in physics, but it really does. So much of our understanding of modern physics, conservation laws, has to do with conservation of angular momentum. Of course, when we do know that it matters is when we talk about things spinning. Remember kind of the analogy of the ice skater that pulls their arms in and spins faster, or the idea that as a stellar nebula collapses into a planetary disk and then into a star itself, the rotation rate goes up and up as the radius decreases. That's conservation of angular momentum, which might seem to have nothing to do with this, right? But it turns out that it does, because not only is it conserved, it's also quantized, which goes into quantum mechanics. So fascinating, complicated stuff. And indeed, the neutrino is a strange beast, but very, very important actually, and also crucial to our understanding of the sun. Anyway, we'll get back to that later. So now we want to move on to the light that is produced, because if we look, we see that there are gamma rays that are coming out of this process. And we actually don't see them until the second step. So here's kind of a summary of them. So we haven't moved on to the second step. So we got gamma rays, just pointed out here that they generally get created during this chain reaction that, of course, finishes with the production of helium. All right. So the gamma rays, by the time they make their way to the surface, are no longer gamma rays. If you recall from chapter 15, we pointed out that in the radiation zone or layer of the sun, that's where you have this sort of downstepping of frequency and photon energy from gamma rays to ultimately visible light. That's happening. Okay. And it's a real long process. It takes a long time for those photons to actually make it up to the convection zone, and then of course the photosphere itself. But the one thing that produces gamma rays that isn't really even shown in the chain. Let me see if it actually is. I don't remember if it showed up. Oh, okay. So it's kind of these offshoots, which is actually kind of a nice way to show it. And when I go back to the slide that I was just at a moment ago, they describe this as step 1.5 because it's a side step. Okay, it's not part of the main chain because the main chain is going to go this way, right? Because we're heading towards that final product of the fusion, again, helium. So over here, this is not heading that way, right? This is literally on the side. And so why even show it? Well, because it is a major contributor to the light that's produced. Okay, and not all the energy is light, by the way. The energy that's carried by the neutrino is pretty significant, and also the kinetic energy just carried by the produced helium is a huge portion of the energy. And but it's not really energy that's going to directly make it to the surface. It just kind of keeps the core hot. So in some sense, we don't care about it as much. But the gamma rays are not the majority of the energy produced by fusion. A lot of that m equals mc squared is going to the kinetic energy of the product of the fusion, which is often not appreciated, or just because it, like I said, sometimes it understandably isn't the focus of the discussion. But anyway, looking at this side step and seeing that positron, again, remember that particle that has to be created because of conservation of charge, well, what happens to it? Well, the thing about positrons is we don't see them, in day-to-day life, because every time they encounter an electron, and mind you, there's a lot of free electrons out there. Think static electricity, right? Current. The world is full of free electrons. Even space is full of free electrons. Think solar wind. So every time a positron meets an electron, what happens is a little thing called annihilation, which is a super dramatic name, but really describes it well. Because what happens is the mass just disappears. The two particles just completely annihilate each other, and no mass is left. So this is a all mass to all energy reaction. It's not like it's not like fusion where there's some mass coming in, some mass coming out, but there's a difference. Here, the difference is all of it. So all the mass that goes in gets turned into light. It is a pure production of energy from mass. Okay? Matter, antimatter, annihilation. In science fiction, it's a popular concept for like drives of spaceships. They talk about antimatter drives. Well, this is the mechanism. It's a real thing. It just has never been scaled up, or realistically with modern technology, current technology could be scaled up to actually be a means of propulsion. But maybe in the distant future. And you got the two charges, right? So charge is conserved because you got a total of 0, because +1 and the -1 sum to 0. So 0 charge in, 0 charge out. And then, of course, the energy matter continuum is conserved, right? It all becomes a gamma ray. And where's this electron that happens to be around to annihilate the positron? Well, okay. No, there's no electrons that are actually attached to the atoms. It's all plasma. It's all way too energetic. But there's still electrons around inside of the core. They're just very much not attached to anything. Okay? And so they are, they exist inside the core, or at the very least in the radiative zone. And there are plenty of them that do exist and are available for annihilation. They're just kind of trapped there, been completely freed from their nuclei, and just waiting around to annihilate, and therefore be annihilated themselves. Although not all of them, of course, will be used up within the lifespan of the sun. Far from it. There's that product, the gamma ray, entire mass. All right, as I said, all right, and then each gamma ray photon has energy equal to the mass of one electron. Yep. And so that's the energy equal to the mass. All right. So we're not saying the photon has mass. The photon is massless. A gamma ray is a photon. A photon's a particle, but a very special particle. It's the only massless particle that exists. Every other particle has mass except photons, because light does not have mass. Okay, now officially step 2. Now you got that deuterium. Remember, it's just going to now collide due to that 15 million Kelvin with another proton. So we're taking another one of the same kind of building block inputs, and now we're smashing it into the product of step 1. What happens? Well, we get helium-3, yet another isotope of an element. Okay, in this case, an isotope not of hydrogen, but of helium. And also a gamma ray is produced. All right. So we have this conserves the energy in the proper way that this nuclear process works out. And we're told here, gamma rays collide with particles on their way out of the sun. They get converted into lower energy photons on the way. So this is that stepping down of frequency, the lengthening of the wavelength. So that's kind of what's being shown here with the different waves. Okay, so hopefully that makes sense. This is just an intermediate step, but on the way to the final product, which is step 3, the actual helium-4 fusion. So we're going to take this helium-3, an unstable isotope of helium, and from another, set of steps that led to the same point, a second helium-3 will come together so that the two helium-3s will fuse together and produce helium-4 and 2 extra hydrogens. What's going to happen to those extra hydrogen 1s, i.e. protons? Well, they're going to go on to restart the chain somewhere else, right? They're just available to continue on for as long as there's enough hydrogen for this whole thing to work, which we now know is in 5 billion years from now. So the leftover protons go on to other proton-proton chains. So that way it's a sustainable chain reaction. So the state of matter for the sun is, well, I've said this so many times, I'm going to tell you, it's a plasma. All right. So what defines a plasma? Quick slides to clarify what I've stated a few times in words. So a gas, by definition, are particles that move around independently. So gases, unlike liquids, don't have defined volumes. All right, they don't have a defined density. A liquid has a defined density, a defined volume, but not a defined shape. Solids have both a defined density, volume, and shape. Okay, so gases are just, they'll expand freely, right, if you let them. A plasma is just that. It's just a gas, but it has lost all of its charge. Okay, so at least it's lost all of its electrons, which means now it has a net charge because the gas is neutral because the electrons will balance out the protons. So gases are neutral, plasmas are ionized, which means they have net charge because all the electrons have been lost. The losing of electrons is just because of the higher energy of the plasma. It's just they're too energetic to hold on to electrons. All that bouncing around, if it's fast enough, breaks off the electrons. We can't see the sun's interior directly, so rely on models that best fit our available evidence. Models assume that the sun is plasma, stable, right? Not cooling down, all right? All three of these things, okay? Yeah, so assumes it's the plasma, right? That's our, definitely has been, this assumption has been tested like any good assumption in science. Any good scientist will test assumptions in as many independent ways as possible. Stable, so it's in some sort of equilibrium, and then not cooling down, which means that the energy loss to the light streaming away, as well as the solar wind, which carries away a small but measurable amount of the overall energy. It's really tiny compared to the amount of energy that's being carried away by light. But all of that is constantly being replaced by fusion. So there's an energy balance. Energy out, the surface equals energy out of fusion. And then the gravity attempts to make the sun, well, that's the thing about the equilibrium, right? The stable part. So no large-scale changes. Well, all stars, our sun included, have this balance between gravity and, which is inward, to give it away. You're welcome to answer it, but I won't check. And the outward balancing force, which is the fusion pressure, which is just a thermal pressure. So gravity wants the sun to contract. If it was up to gravity, the sun would just collapse into a black hole. But there are quite a few things that will stop it from doing that. And which, to foreshadow things to come, lectures to come, chapters to come, to get a black hole, you need a lot of mass and you need just the right conditions. And because otherwise there's a lot of backstops, so to speak. There's a lot of forces that will prevent gravity from collapsing to that ultimate singularity. And in this case, the pushback against gravity is just the fusion itself and the outward pressure that's associated with that thermal process, that heat process. So gravity seeks to contract, and the outward pressure of the hot gas balances it. So we say that the sun is in a hydrostatic, because it's acting in a fluid way, all right, equilibrium. It's the balancing of these two effects. So small changes inside the sun are self-correcting. Is often described as the solar thermostat, or the way that this is a stable equilibrium, the type of equilibrium where if you make perturbations away from it, then the forces that pop up will restore to the original state. All right, so if the sun contracts a bit, what happens to the sun's interior pressure and temperature? Now, I'll let you answer this one, and I will check, see if I get some answers from you all. Because this is the type of question that you're almost guaranteed to see in a quiz, on a test, these types of what I call the solar thermostat questions. I call it a solar thermostat because it works in the way that a thermostat does, right? It adjusts to keep the temperature constant. So we're being asked here, if it contracts, right? If it's like, so the contraction just happens for some reason, right? The sun just, for whatever reason, sort of spontaneously contracts. Well, does that mean it's just going to run away and keep contracting? Does this doom the sun? No. So then what's going to happen, right? How will the sun's interior pressure and temperature respond to a sudden contraction? Will the temperature go up and the pressure go up? Okay. Exactly. They both will go up. The core will become hotter, and that means that it will produce more pressure. Okay, so that means that that outward pressure will undo the spontaneous contraction. So a spontaneous contraction will just be counterbalanced by the uptick in temperature and pressure, which is just an immediate consequence. And then that causes it causes an expansion, undoing the contraction until equilibrium is restored. All right, so this is talking about which experiences the greatest pressure. So this is pressure as it relates to depth. The deeper you go, the greater the pressure. This is, idea with oceans, certainly true of the sun as well. The core experiences greater pressure. I've mentioned this idea many times. It was an explanation for the layers of the Jovian planets and so on. All right, so which best illustrates the gravity and pressure of layers at different depths, right? So is it like, big arrows at not a very big depth and small arrows closer to the core, or the opposite? Well, think about it. Probably no. Okay. It's going to be this. The arrows, which represent force or pressure is just force per area, so they're very directly related, grow with depth. They grow as we approach the center of the sun. So temperature and pressure increase closer to the center of the sun. If you remembered these graphs from chapter 15, of course, neither of them was pressure. It was density and temperature. But density, although it's not equivalent to pressure, well, what creates the greater density? Why does the density go up as we approach the core and the center? Well, because the pressure compacts the material. So there is a direct relationship. Okay, so the energy equilibrium, as I said before, is that the energy lost as light is replaced by fusion in the sun. The energy produced from the process of fusion, that proton-proton chain, is equal to the energy flowing out into space. All right, so a high energy photon is produced by a nuclear reaction at the center. This energy will leave the sun. Soon after is a high energy photon. Soon after is a bunch of low energy photons. Much later as a high energy photon, or much later as a bunch of low energy photons. So I sort of hinted at this, and maybe you can reason it out. This hasn't been spelled out, so it's not one of these questions where you can say, oh, hey, if you've been listening, you would know it right away. But definitely what we talked about, you can think about the energy of the photons I've explicitly said, as have the slides, but the time I've only hinted at. And indeed, it's much later. If you answered in the chat, it's great. I haven't had a chance to check, because it's just a very long process. It takes many, many years, thousands to up to 1,000,000 years for an individual photon to, produce many other photons, and eventually that final product of emission or absorption and re-emission many, many times actually carry that energy to the surface, or at least the convection zone. That process is incredibly slow because of the high density of the radiation zone, right? That material that I sort of said was analogous to glass in terms of that the heat flow was not conduction, counterintuitively, which you would think through a solid, but actually radiation itself, acting like a big transparent level or layer of the sun. Regardless of all that, what you do want to know is that the process does take a long time. So you have a very slow process. The light that we see at the surface is light that was related to fusion events that occurred hundreds of thousands of years ago. So there's no like direct window into what's happening in the core, at least in terms of the light. So a photon is created in the core by nuclear fusion as a photon is created in the core by nuclear fusion. Oh yeah, as a gamma ray. You know that? So that's all of the light that's produced. Every type of light. So there's multiple steps, including that side step, annihilation of the positron when it collides with the electron, interacts with an electron. Well, every time the light that was produced was short enough wavelength, high enough frequency to be considered a gamma ray. So that exclusively gamma rays. Right? So a photon is created in the core by nuclear fusion as a gamma ray. Moving away from the core, the atoms enter the blank zone layer where the most important method for heat transfer is, well, it's the same word twice, radiation. Okay? It's that radiation zone. It radiates through that high density layer of the sun's interior. In the radiation zone, most atoms are still ions, so it's still a form of almost metallic plasma because it's compacted into a solid. So the photons are rarely absorbed. The layer is transparent. Okay, so it is a transparent level, and that's like kind of an interesting idea that they're rarely absorbed. So they're essentially just ricocheting around. So you have this case where they're just moving around because there's not any energy levels that can accept them. There's no way for them. A big molecule can vibrate in so many ways, and a solid can vibrate in so many ways that it's able to accept just about any energy level. But these atoms really can't. And so the way it behaves isn't even quite like a transparent window so much as something else entirely, where it's like a plinko board or whatever, right? Where you have to bounce past all these separate little barriers. And that's what the photon is doing. So the photons scatter off of the nuclei. Think pinballs bouncing off of obstacles. And so the path is this incredibly circuitous, back and forth, random walk of a path. And this is kind of a term that gets used in statistical discussions. And it means that's why it takes so long, why it is rightfully considered a very, very slow process for the photon to actually make its way out of the sun. The granulation on the photosphere indicates that the energy is moving outward, right? Well, this is just a review. Hopefully you remember from 15, it's convection. Okay, so not radiation, but convection that's occurring in the upper levels of the sun. So the sun has 2 out of the 3 means of heat transfer occurring. Radiation in the interior, convection near the surface, radiation into space, and the only thing that's missing is a significant amount of conduction. And that's because conduction requires molecular vibrations, and it's just not going on here. Too hot to have molecules. In the convection zone, photons are absorbed and heat the gas, which rises to the surface by convection. So here that photon, which has now transitioned to a lower frequency, lower photon energy type of light, is finally able to be absorbed. All right. And the surface, so it's cool enough for some atoms to form, which can absorb the photons. Okay, so we actually have some absorption, and we say cool enough, so we have a state that is not a pure plasma. All right, so you see that electron? So that would be kind of going to a atomic rather than just nuclear state. And that those terms get used that way sometimes, where atomic means non-ionized, nuclear means fully ionized. Absorption slows down the photons, which traps heat in the gas. The hot surface rises towards the surface. So you have these huge plumes of hot rising, gas in the convection zone. At the photosphere, the density of the atoms is very low, and that's where the photons at this point corresponding to the continuous spectrum at a peak wavelength of, 570. I don't remember off the top of my head, but corresponding to a temperature of 5,800 Kelvin and wavelength, I think 570 nanometers, or 540 maybe. But anyway, around there, can escape into space. Okay, so now we have that radiation into space, as I said before. Now, if there's a huge time delay, if we want to look into the sun, it's opaque, and we also know that any light that makes its way to the surface corresponds to a core state that is, like I said, hundreds of thousands of years old. So the core could be doing something very differently today, and we wouldn't know, right? That's unlikely, since our model suggests that the sun is stable and will be stable for not just hundreds of thousands or even hundreds of millions, but billions of years to come. But scientists would still like to know, even be reassured, that the core of the sun is doing what we expect. So how can we, if we can't see into it directly, study the interior of the sun? One way is with vibrations, helioseismology, looking at surface patterns and matching those to models of how those vibrations would transmit through the body of the sun. All right. So this is kind of like the way that we discern the levels of Earth by looking at seismic waves. There's less ways to independently confirm this sort of thing, but there's one that we will mention, and certainly it's a necessary and important way that we can study the sun by looking at the surface. All right, let's skip over that. So we've learned about the differential rotation through helioseismology. All right, it's helped us understand the width and nature of the radiation zone. The amount of hydrogen and helium is the same at the surface as inside the star until you reach the core, at which point the values change. It's helped us understand sunspot causes, such as the cool sinking gas under sunspots that act like a plug to block hotter gas from rising. And the confirmation of this science and measurement technique of helioseismology is neutrinos. And what I mean by that is that it's so crucial in science to have like two separate techniques of measuring something, because that way you can really test your assumptions that you made with your one measurement. And if you don't have two separate ways to measure something, then you do your best, but you can never really know for sure if your assumptions are right. And so the other way that we can really figure out what's going on inside of the sun goes back to those neutrinos, that weird byproduct of step one of the proton-proton chain. They were originally hypothesized to exist back in the 1930s, all right? And then notice that momentum is mentioned, as I hinted at before. And then they were confirmed years later. The long-running understanding of them, which has been confirmed many times over, is that they don't interact with matter very much. Really, they can just pass through matter. They escape freely from the interior of the sun at nearly the speed of light. That's a pretty minimal interaction. Remember, the photons take years, tens, thousands, 100,000, up to 1,000,000 years to make their way out. A neutrino just heads out in a split second. Well, does that mean that we can even detect them? They interact with matter so weakly, then how do we even confirm they exist? Well, they're very difficult to observe for the very reason that they're able to pass right out of the sun, making them quite interesting to us, because they would tell us what's going on almost instantaneously inside of the core of the sun. How the heck do we catch them? They are very light, they have a neutral charge, and they move very fast. They're ghost particles, sometimes called that. It's really, just plainly put, a very difficult thing to do. All right. And so you got to get it just right. So you have this tiny chance of them colliding with a nucleon. Okay. And when they do, they can change the type of the nucleon. They can change it from proton to neutron or vice versa. All right. So, because they can cause a chain reaction and go vice versa. So changing which nucleon will change the type of the atom there is. And so you can have a proton to a neutron or a neutron to a proton. In both cases, the actual element will change because the atomic number will change. So when a neutrino collides with a nucleon, it changes the nucleon's type, therefore it changes the elemental type. So if the change is a neutron to a proton, then you of course have one extra proton. If the change is proton to neutron, then now you have one fewer proton. Okay? So if you know the neutron was there by detecting the results of the changed atom type. So neutrinos can also bounce off of an electron, which causes an emission of light. So it is known, you know that the neutrino is there by detecting the light from the electrons. Oh yeah, and this I can see, yeah. This meant to say, no, the neutrino was there, not neutron. Neutrino, easy typo since the words are similar, but no, the neutrino was there by detecting the results. Okay, that's the idea. And here you can detect the emitted light. So these are a couple of the ways that you can detect them, but again, the chances of either of these things happening, colliding with an electron or colliding with a individual nucleon is, as this, cute animation showed, very unlikely. Missed. Hey, so you got a 1 in a, tiny number, 1 in a 10,000th, 1 in a 100,000th chance. So you have to build these huge vats, these huge tanks full of carefully balanced material that can, register a change in one atom, okay, or the tiny emission of light. And they do them underground, primarily miles underground in abandoned salt mines, decommissioned salt mines. There's a few of these neutrino experiments throughout the world, some in the United States, some in Japan, I'm sure elsewhere as well. Okay. Homestake experiments, 1960s. They had chlorine atoms, 100,000 gallons of chlorine. All right. And you have 45 times 10 to the 10 neutrinos per square inch passing through the Earth every second, but most of them just pass right through the Earth, the whole planet, without even slowing down. Of that number, right, this unbelievably large number, 450 billion, if I was to say this in words, one out of that 450 billion, and that's every second, right? Well, you multiply that by the number of seconds in a day, and you get one that interacts with anything, any matter, period. And then what are the chances of interacting with this small tank? Sure, it looks huge. There's a person for scale, by the way, but small compared to the whole Earth, isn't it? So you have to be very patient. The first detection in 1956 led to a Nobel Prize. All right. And another one, because of follow-up results and actually counting the solar neutrinos in the 1960s, led to a Nobel Prize in 2002 after the results were studied. And they actually found out that there were much fewer of the neutrinos than they expected once they actually had enough to really have good results. And that either meant that our models of the sun were fundamentally wrong, or it turned out neutrinos behave differently than we thought. They actually change. They oscillate between something called flavors, which are like states. And so that allowed us to understand neutrinos a bit better, and therefore finally be able to effectively use them as a detection method of looking into the interior of the sun, which now we can kind of feel like we can do accurately. So we had a total of 4 Nobel Prizes associated with neutrinos. Quite a few, right? Because it's such a challenging but important particle to study. All right. So that will wrap things up for today. We'll finish 7 minutes early.